he then went to University of Virginia, where he was a graduate student working with John Hawley. He helped to test and develop some of the Athena code. Since then, he's finished that up, and then he moved to Colorado, where he is now as a Sheila fellow. He works a lot on accretion disks, protoplanetary disks, working with Phil Armitage and Chris Beckwith and collaborators. If those of you here for Phil's talk in the fall, he showed a lot of work that was really, a lot of it was Jake's work. So if you remember that, Jake was sort of the credit for that. So today he's going to talk about turbulent linewidths and protoplanetary disks. And I'll let it go.
All right, thanks Shane for the introduction. Yeah, so I guess if Phil Armitage was here in the fall, you may recognize some of the figures.
I need to be reminded.
Yeah, you need to be reminded. Okay. So yeah, he's obviously one of my collaborators, and I also work with Mary Hughes and Dr. Forg in this sort of project. So as a graduate student, I mainly worked on accretion disks in sort of a general sense, and that included black hole disks as well. But since then, I moved on to more protoplanetary disks, planet formation, that sort of thing. And one nice thing about these systems is that we can actually resolve them spatially using infrared or optical or radio sub-millimeter imaging here, as opposed to seeing X-ray binary disks and not actually resolving the event horizon or anything like that. So this will become sort of useful later in my talk, but I just wanted to motivate that, especially with the advent of ALMA, this is definitely going to be a good thing to study these systems. So, sort of a brief introduction. We all know that protoplanetary disks play an important role in two ways, really. Accretion onto the central star, so formation of the central star, all the way from sort of the highly self-gravitating class 0 sources like what Caitlin works on or has worked on, to later on T-Tauri phases, which are more like isolated disks. But these systems have typical accretion rates in the range of 10 to the minus 8 solar masses per year or so. And here's actually an early work. This is a paper done by Phil that I was part of. I've since worked a little bit on as my undergrad thesis, but it was the same idea, which was to study the origin of FU Aureale bursts in protoplanetary disks. But anyway, the main point is that there are 1D models that account for all these disks, and you can see how mass accretion plays a role onto the central star from these disks. But of course, we all know that these disks are the birthplaces of planets, and so there's a lot of physics in this cartoon that I'm not going to talk about. But the basic idea, of course, is to go from sort of nice, well, at least from a physicist or a theorist mindset, nice sort of cartoon disk, and the dust settles out, and something happens, something happens, something happens, and you get down to planets eventually. There's been a lot of analytic work and a lot of work in general on studying these processes, especially what I'm going to focus on early on, in the context of laminar disks, where the fluid is not really doing much other than orbiting around the gas and then sort of spiraling inwards. And that's sort of what it does, but it turns out that these disks are actually more likely to be turbulent than they are laminar. And this disk turbulence is intimately tied to the transport of angular momentum. And so this is because the microphysical viscosity of the gas is way too small to account for the observed accretion rates that we see. And so quite a few years ago now, Shakura and CITA, although they were talking about disks around black holes, suggested that there was some sort of turbulence. They didn't know what the cause of this turbulence was, but it was stirring up the gas, and this gas, or this turbulence, led to an enhanced viscosity, which would act in a sort of similar way as microphysical viscosity, which would cause diffusion and angular momentum outwards and mass inwards onto the central star. And this is the development of the so-called alpha model, where the viscous stress tensor, or the turbulent stress tensor, I should say, is proportional to the thermal energy and the constant of proportionality is this alpha here, which any disk theorists will have heard about at some point in their lives. And so this is a dimensionless quantity that quantifies how much angular momentum you get. So, and the alpha model suggests the basic scaling. This will also become somewhat important later on. That the turbulent velocity, this is the turbulent velocity departure away from pure Keplerian rotation, scales as the sound speed and within the alpha to the 1/2 power. And so that's the basic idea of alpha theory, or that's another way you can write down alpha theory, is that you get sort of this relation. Okay, so there are, in my mind, sort of 3 likely sources of turbulence in these disks. And I'm going to talk about 2 of them today. I'm not going to talk about the subcritical clinic instability. For one, I haven't studied it in detail. For 2, I'm not yet entirely convinced that it works in protoplanetary disks. It actually needs a specific radial entropy profile and a specific set of the way that, or a specific thermodynamic behavior that's rather narrow from what I understand. So if it deviates too much, then this thing doesn't work. And so it's not particularly robust. And there's also some debate about its relevance in actually existing and having the right entropy profile in low mass irradiated disks. Although it's something to keep in mind because, well, as I'll talk about, there are regions of low ionization in protoplanetary disks, and so you might need some mechanism like this. The second mechanism I'm going to talk about is self-gravity. This is mainly important very early on, such as like what Caitlin was working on, or for very massive disks, and or potentially a large enough radii, depending on what the surface density is, and the temperature and that sort of thing. And then finally, the magnetorotational instability is probably thought of as the most likely candidate for generating this turbulence at late times in the disk's evolution. But the problem there is that it requires sufficient ionization levels. The gas has to be well coupled to the magnetic field. I'll describe that a little bit more in detail. But these are the 2 mechanisms I'm going to talk about in this talk. So first, starting with that magnetorotational instability. Basically, if you, well, I just played this movie here. This is by John Hawley 12 years ago now. It starts off with, see if I can pause it, with a sort of a donut of gas, and this is the log of the gas density. You can't see it here, but there's magnetic field lines that thread the torus here, and the magnetic field is relatively weak compared to the gas pressure. And when you and it's rotating around a black hole in this case, what you can see here is that the gas rapidly becomes turbulent and stuff starts to accrete inwards. And despite being a little bit pixely, I mean, the simulation is a bit dated, I still think it's my favorite simulation of the MRI, just because of the zooming out and all this cool stuff here. But you can see it's sort of flattened into a disk, which has actually turned out to be a Keplerian disk, and it remains turbulent and accretes stuff inwards so long as there's a gas spore. Of course, some stuff moves outward and carries most of the angular momentum with it. So the magnetorotational instability, especially in well-ionized systems, works very efficiently to transport angular momentum, and you get typical alpha values of about 0.01 or so. That's sort of what our work is, various people's work is converging on it as far as the alpha parameter. Now, self-gravitating turbulence, this is a movie that my collaborator and I, Duncan Forgan, from our paper that we just submitted. This is an SPH calculation using 500,000 SPH particles. There's a lot of initial transits here. So this is a mass of the disk is a quarter of the mass of the central star. So there's a lot of initial transits, but eventually it settles down into sort of a gravido-turbulent state, where now angular momentum is no longer being transported by magnetic fields. It's being transported by the spiral arms, the spiral density waves, and basically the gravitational turbulence itself. So I would say now, it took a while to get here, but now is about where it's in a gravido-turbulent state. And one characteristic that is sort of similar between these 2 mechanisms is its tendency to create these sort of spiraling arm structures But that hasn't been compared in detail between the two mechanisms. It's obviously going to be more important for larger mass disks, as I'll show later on, because self-gravity tends to produce large spiral arms. But what I am going to focus on are new sub-millimeter observations from which you can extract turbulent velocities of the gas. And so Meredith Hughes did this in her recent paper in 2011, where she looked at two systems nearby, TW Hydra and HD 163296, and she looked at the CO3 to 2 transition line in the sub-millimeter using the SMA, and basically was able to probe, she looked at the line, rotational lines of this gas, or sorry, just the lines of this gas where the CO becomes optically thick, which is very in the upper, about, I would say about 4 scale heights or more above the disk midplane. And so I'll come back to this picture later, but her observations were primarily probing sort of the atmosphere of the disk. And the way that she extracts the temperature is sort of best described as follows. You have a model line here, so this, the delta P represents the broadening due to rotation, and there's some broadening due to thermal emission as well. The adding in turbulence is not the same as changing the temperature. The two are not degenerate. And in fact, when you vary the parameters, you can see from this plot that the peak to trough ratio changes depending on whether you change the temperature or the turbulence. And the basic idea behind that is that in the Rayleigh-Jeans limit of the spectrum, increasing the temperature will increase the brightness of the line as well as make it broader, but turbulence will just redistribute the flux in velocity space. So through that, you get a non-degenerate way of extracting the temperature from a model line. And so here's the actual data. She matched, in her work, she matched matched the data to 2 models. Del Asio model, et al. Model, which is a basically radiation transfer model for matching, setting up a hydrostatic equilibrium model disk and comparing that with observations, and a similarity solution where things generally drop off as a power law. And in both cases, in HD 163296 and TW Hydra, she did a best fit model for both of these to extract the turbulent broadening from the line. And there's also the no turbulence line somewhere here for reference. And so the values that she got out were, and she put them, I like working with Meredith because she's an observer that thinks in terms of, or she can think in terms of theory, in which we do everything unitless. And so she did put this in nice dimensionless numbers and found that typical turbulent broadening in terms of the sound speed was about 0.4 for HD 163296, and she found an upper limit of 0.1 for TW Hydra. And this was in sort of the outer disks because the SMA doesn't have enough spatial resolution to go close in towards the star. So this is taken at about 100 AU or so away from the star. So our primary goal is to analyze protoplanetary disk turbulence from first principles using both self-gravity as a mechanism for driving the transport as well as the MRI. And then also you can use these results to compare with current observations and make predictions for future observations, particularly those that will be done with ALMA. In fact, we're working on our ALMA Cycle 1 proposal regarding this work. Okay, so let's first consider MRI-generated turbulence. We use the state-of-the-art Athena code. Like Shane mentioned, I did some development of this code for my graduate work. I worked with Jim Stone and John Hawley on this. It's a publicly available code. You can just Google Athena code or Athena NHD and you'll find it. And in this, for the MRI simulations, we use what's called a local simulation, or the shearing box approximation, in which case we examine a small chunk of the disk. We pick out a small chunk of the disk, so small that you can ignore curvature terms and set it up in a Cartesian geometry. And now we're co-rotating with this box around the central star. And so since we're co-rotating, we have to set up a shear profile that you can see from here that accounts for the Keplerian rotation of the gas. And we added in, of course, the appropriate source terms corresponding to radial gravity, centrifugal force, and the Coriolis force. And then, of course, we just solve the equations in MHD. This is generally valid as long as your scale height, or actually the size of your domain over the radius away from the star is much, much less than 1. You can expand the equations in this approximation. And in all these simulations, we assume that the gas is isothermal, so we don't treat any radiative effects yet. Okay, so like I mentioned before, studying the MRI in the context of black hole disks is nice and easy, because you just assume that the gas, it's easy to do with ideal MHD codes because the gas is just perfectly well coupled to the fluid. But in the case of protoplanetary disks, there are 3 non-ideal MHD effects that become important as a result of the low ionization fractions that exist. These disks are colder than X-ray binary disks, for example. So the 3 effects are ohmic resistivity, the Hall effects, and ambipolar diffusion. And you can sort of think of it in this way. So in the ohmic resistivity regime, which happens at larger densities, the electrons and ions, whatever those ions may be, whether they be just hydrogen molecule, or just protons, or some sort of ionized species, they collide with the neutrals so frequently that they aren't very well coupled to the gas. The gas just slips through the magnetic field, and it acts like a diffusive process. And at the opposite end of in the opposite limit, at very low densities, you get electrons and ions are actually well tied to the magnetic field. But because it's so low density, there's very few collisions between these guys and the neutrals, which take up most of the gas. And so in that case, you may have the MRI working just fine on the magnetic, or on the electrons and ions, but it'll still sort of act as a diffusive process because the neutrals won't see much happening, it won't see much action. And in between, you'll have the Hall effect where one bit, the electrons are tied to the magnetic field, the ions are tied to the neutrals, and so you get an additional EMS force due to that. I'm going to be focusing mainly on ohmic resistivity in this talk. I will mention ambipolar diffusion. The Hall effect is in development as far as our code goes and understanding its effect on the MRI. And just to sort of put that into more quantitative terms, this is a density temperature plot, and these are the 4 sort of regimes. Actually, I would count it as 3 because the middle 2 are where the Hall term dominates. And at the highest density, ohmic dominates, in the middle, Hall dominates, and further out at low densities, ambipolar diffusion dominates. And here is for minimum mass solar nebula, the conditions at the midplane out to 100 AU, and at about what we would sort of call the surface, which is 4 scale heights above and below. And putting that into more of a cartoon picture, as a theorist, I love cartoons. So we have sort of 2 regions. The Hall effect is not on this diagram. Again, we don't fully understand where it operates. It sort of operates at intermediate density. So I'm just going to point out the 2 extremes. Well, first of all, close to the star, it is hot enough for the gas to become collisionally ionized, or at least the alkali metals are collisionally ionized, and so you get enough free electrons for it to behave like it's in the ideal limit. Further out, things cool down, and you get but you're at high enough density that the ohmic resistivity becomes important, and so you get what's called the dead zone. Above and below the dead zone, you're ionized to a certain depth by non-thermal sources such as X-rays from the stars, or cosmic rays if they're unshielded from the stellar wind, and maybe even UV photons from the star. Further out, you can get lower columns and lower densities, and so ambipolar diffusion will dominate, although it could be the case that even despite this, you still get full ionization of the disk, depending on the conditions of exactly what you have. But if the ionization sources can penetrate all the way through, then you can get full ionization of the disk. There's still some debate about exactly what the conditions are out here. If you ask Eugene Chang, and I am working with sort of one of his models, he'll say that most of this is dead out here because ambipolar diffusion is so strong. But others may disagree. He argues it in the context of PAHs soaking up a lot of charge. So, but for most of the talk, I'm going to treat this region as ideal MHD, and I'll have one little bit about ambipolar diffusion. And so, well, I don't really need to show you these plots, but I will just for the sake of completeness. The turbulence stress, which is this is the equivalent of the alpha parameter, increases with decreasing resistivity. So resistivity increases to the left, and so you get an increase in stress. And below that critical magnetic resonance number, as defined here, you get no turbulence at all. So the resistivity just completely quenches away the MRI. And the same thing is true for ambipolar diffusion. Piece of paper by Rye and Stone, except they find that there's always a minimum stress level, although it's getting so small down here, it's probably not going to even matter. But that you get a general trend with, as you decrease ambipolar diffusion, then you make the stress stronger. And he and I are working on a paper together to further study this effect. This was a rather simplified simulation. We're going to make a more advanced simulation with vertical stratification and studying the net vertical field and a vertically stratified disk with ambipolar diffusion. But getting back to the model that I've set up, we just assume a minimum mass solar nebula model and calculate the ohmic resistivity at all heights and radii. And we balance these ionization sources against simple gas phase recombination at all radii heights. So we don't have any dust physics anywhere that's soaking up charge. This is sort of the base thing that you can do, the simplest thing that you can do. And so we have stellar X-rays. Actually, aluminum shouldn't even be on here because it contributes anything, but it does penetrate all the way through. X-rays go down to about 10 grams per centimeter squared before it dies off significantly. And cosmic rays go further in, but they have a lower ionization rate. So balancing these two sources again, and I don't have any UV photons in that particular model. So balancing that against gas phase recombination gives you a resistivity profile. And we set shearing boxes, our local simulations, at star level locations. One really close to the star, which will be like ideal MHD, and one out here, which will also be like ideal MHD, because again, I'm not including yet ambipolar diffusion. And so when you don't include that, you do get a significant penetration of the non-thermal sources through the disk. And then two that are sort of in the dead zone region. The one that's definitely in the dead zone region. The one that's sort of in this, obviously on the cartoon it's the transition region, but it does turn out to be at a transition region, as I'll show in a minute. So here's two movies. This is the magnetic field and turbulence for one of these ideal MHD calculations. And then here's this similar simulation. They're slightly different block sizes, but that doesn't matter here. And you can see the prevalence of the dead zone here, where you get very little, if any, magnetic activity. And then you have some magnetic activity up in the upper layers, and that's producing some stress, although it's lower stress than in this guy.
So here's this sort of edge effect to the left.
Oh, this bump?
Yeah.
Yeah, that's a transient. I should really redo this movie. So this movie needed a really high temporal resolution, which meant I could only focus on like half an orbit to make a movie. And so this is just a transient, and it goes away eventually. So I've had people ask me about that before. So thank you for that pointing out. Okay, so from our local boxes, it's actually pretty easy to extract the turbulent velocity because we've already removed the rotational component of the box around the central object. And in our simulations, I forgot to mention this, we have orbital advection turned on, which means we solve the equations of MHD separate from solving the equations that just account for the linear shear of the flow, or the Keplerian shear of the flow. So basically, we just extract the velocities from our simulations directly, and what we do is we separate it into two components. One is the vertical motion of the gas, which is just VZ. The other is a azimuthally averaged form of VR and dphi, based on looking along a line of sight and then averaging over a disk. And so you get a representative value averaging time, and we also density weight this to account for the fact that more material will, you'll see more of the denser material if your optical depth can probe further enough in. And so let's first consider the limit of ideal MHD, again, close to the star, but it's also useful as a starting point. before adding in more complex physics. So I'm of the strong belief that you always want to start with as simple as you can before going up in complexity, so that you know what your model is actually doing. And in the ideal MHD limit for this size domain, h here is just the vertical scale height, you get this distribution of velocities for different depths into the disk. So this might take a little bit of time to explain, but it's worth understanding. So first of all, the dashed line is the vertical velocity component, the up and down motion, and the solid line is the horizontal in-plane averaged component of the turbulent velocity, like I described. And we density weight this, but for z greater than 3h, we only integrate down, if you were to like look onto a face-on disk, only down to 3h above the midplane. And then the red guy is 2h down, and then the green guy 1h and 0h is essentially going for the entire disk, because most of your mass is at the midplane anyway. So basically what this is showing is that if you were to look at different optical depths into the disk, you would see a different distribution of turbulent velocities. Another thing you'll note is that it's quite a wide distribution of turbulent velocities, and they all have peaks and that shift outwards, so that there's an increase in velocity as you move vertically outwards, and the whole distribution moves over, but it is quite wide. So wide, in fact, that near the top of the disk, you get about 10% of the distribution is in supersonic motions. So you get supersonic motions being picked up by the turbulence, which is interesting in itself. So moving on, yeah.
Do you have to put in a density floor to do this simulation?
Yes, we do have to put in a density floor to do the simulation, but I did, and I checked to make sure that that was not contributing to this. Because so you have to pick out certain bits of your simulation. If things are sort of quiescent, then your density floor gets hit, and then you see some weird spikiness that comes out. And actually, that's what I first encountered and realized that. And other times, the density is pushed outwards due to magnetic pressure, and the floor is not hit, and then you get something nice and smooth like that.
If you normalize the turbulent velocity to Alfvén speed, you get an outer distribution.
Normalize the turbulent velocity to Alfvén speed, right? So,
What's the RMS Alfvén speed, right? That density.
right. The Alfvén speed will be roughly constant out until about, oh wait, no, that's not true because it'll drop off with density as well. So yeah, it could be a lesser effect.
I don't think it would be. It tends to go up more strongly than the sound speed as you go up the scale.
Well, the sound speed in these simulations is constant.
Yeah,
Right.
okay, yeah, so then,
Right.
yeah, so I think it probably would.
But maybe it wouldn't be as, let me think for a minute. Well, the Alfvén speed would go, the Alfvén speed is 1 over root density, so it would increase, the magnetic field is also dropping off.
The power not as bad because the density level is less.
Right, it's not, yeah. And in fact, the magnetic energy or the stress actually is sort of flattened and then drops off at about 2 scale heights. So I don't know the exact answer to your question, but it could conceivably be that way, yes. I'd have to think about that a bit more. Yeah, so, okay, so let's step up the complexity and add in some ohmic resistivity and consider these other radii. And so this is a time evolution of this turbulent stress, the alpha value at these other radii. And so at 50 AU, again, without any ambipolar diffusion, you get about 0.01, actually it's more like 0.03, but in order of magnitude. So this is what you would expect in the ideal MHD limit. In the dead zone model, you would get much smaller limits, so this is only the surface layer accretion. Now, what I was pointing out is 10 AU as being sort of a transitionary region, is you get this weird bursty behavior. And that's because you're at sort of I can go into this a little bit more in detail later, or one-on-one if you want, but I don't have a lot of time here. But basically, there's a competition between the resistivity and the shearing of the field out in producing toroidal field, which then reignites the MRI. So you get this sort of competition producing bursty accretion. And I actually have a paper on this from 2011, the last paper of my thesis work.
What's the period?
What's that?
What's the period of that?
Oh, it depends on the resistivity. For pretty strong resistivities, it's about 10 to 20 orbits or so. But it all depends on what exactly the resistivity is. And sometimes you find that it'll stay saturated for a while, and then it'll drop down to a dead state and stay there for a while, and then suddenly come back. And so sometimes there isn't even a well-defined period. So I can explain a little bit more in one-on-one if you're interested. Okay, so the 50 AU guy looks very similar to the ideal MHD case. No surprise there. And sort of the same thing with the 10 AU in the high stress state. I'm only considering that here. But when you look at 4 AU, I mean, this is also not really a surprise. You get a much lower turbulent velocity distribution near the midplane. And that's, of course, due to the fact that there isn't any turbulence there. However, there are waves that are picked up. There is a small Reynolds stress, fluid stress, due to the active layer. So you don't get a zero distribution. It's not like a sharp function over there. It is non-zero. But the other thing is you still get a significant component of the velocity up in the active region, due to the active region pumping things up and potentially also some steepening effects. And so this distribution is very similar to this distribution. It peaks about the same location, the velocity space, and it has a supersonic sort of tail here. And so kind of, instead of looking at these broad distributions which have a lot of lines on them, it might be best to sort of think of it in terms of the change in the surface density over the surface density. So one would be going through the entire column of the disk, and then this is the fractional change outwards. So this would be like the very outer layers. And this is the peak of that distribution. So ignore the red curves just for now, because that had to do with a sort of a control group case in this paper. But the idea here to take away is that in the ideal limit, or at 50 AU in this case, you do get a gradient in the turbulent velocity, but in the blue case you get a very sharp gradient in the turbulent velocity. Granted, there are only so many data points here, but this was a sort of a sparse sampling. We could do better and fill that in the plot. But basically, you get in the 4AU case, you get the same velocities out here, but it drops off much faster as you go looking into that.
Where's most of the accretion?
Where is most of the accretion? So most of the accretion, it depends on where. In the dead zone location, most of the accretion is happening in the surface layers. In the ideal case, it's happening through the midplane. So because that's where most of the mass is, right? And in the ideal MHD case, again, the stress is relatively uniform out to tube scale heights above and below. So uniform stress and most of the mass, that means that there's going to be more accretion there. Okay, so work in progress. I'm running ambipolar diffusion calculations now, and in this particular case at 100 AU, we're running this with Eugene Chang's models now, where we include a very thin layer of ionization due to FUV photons only. In his models, the PAHs are really just soak up everything else. They soak up the charge due to the non-thermal sources. And the only thing you get is free electrons in a very thin layer from the FUV photons. And so you do still get some turbulence, although it is significantly smaller. So you sort of get the equivalent actually of an ambipolar dead zone out even at these large radial distances. And so you can sort of see that here. This looks similar to the ideal MHD plot, but you can see that again the gradient is reasonably strong because you go down to about 0.01 here in the velocity. So this 0.01 is consistent with, actually that's not consistent, I'll go back. So this value around here, 0.1 V over CS, is roughly consistent with the alpha model. So if alpha is 0.01, then you get this is consistent with V over CS being about 0.1. So, but in the case of having a dead zone, you get much lower alphas, but it's still in agreement because you get alphas of like 0.01, and then alphas like 10 to the minus 4, you get V over CS like 0.01. So in the midplane at least, it all makes sense. The MRI turbulence is sort of consistent with what the alpha model predicts as far as scaling goes, but that doesn't necessarily mean that that's what you will observe because, again, so far we've only been able to probe the surface layers of the outer disk, which result in 0.4 for HD 163, 296, and 0.1 for TW hydra. In these outer layers, we get, well, 0.1 to 1, which is an order of magnitude change in the velocity. But at least it's in rough agreement with observations so far. Okay, so I just want to consider self-gravitating accretion real quick, sorry, and then I'll move on to sort of summary, sort of the big picture point that I want to make. Okay, so for these, sure.
That previous thought, so those VOCs, what depths are they? Do they think they're covering?
About 3 or 4 scale heights above the midplane.
Okay.
Yeah.
So that is a little bit comparable.
Yeah, it's comparable. Yeah. Maybe a little bit higher, but I mean our simulations couldn't go much farther. So okay. So yeah. So we use the SPH code. I'm not going to go into the details because I don't have too much time left. Here's the different disks. We did do different disk masses just for the sake of understanding, studying that parameter space. And quarter of the solar mass, or quarter of the central mass, up to 1.5 times the central mass. And you can see that the presence of spiral arms become more predominant as you get larger. So the main goal here is to compare what we see with the same diagnostic for self-gravitating accretion, specifically in the gravito-turbulent case, to the MRI. So, and we use ray tracing. In this case, we use ray tracing to extract the turbulent line velocity. Again, I'm not going to go into the details there. So this is a very similar plot to what I showed. Well, it is the same plot as what I showed before, really. And so the solid lines again are the horizontal turbulent component, and the dashed lines are the vertical. And now, since this is an SPH code, the resolution follows the masses, which is all in the midplane. So we can't go very high above the midplane, unfortunately. So we can't really make a huge comparison with the MRI, which we can study up to 4H or so, with an SPH code. Now, we are going to do some grid calculations where we can do that, because in that case, you have uniform resolution. But at least for these two heights, looking down to 0, down to the midplane, or down to 1H, there's not much of an effect in the turbulent velocity. And there's a huge offset between the horizontal velocity and the vertical velocity, something that did not exist before. Before the two velocities were more or less the same distribution. So there's an anisotropy here where the horizontal velocities tend to be higher. And this is in the case of a low mass, a quarter of the mass in the disk is about 0.25 times the mass of the star. If you go to much larger disks, you get this weird feature that emerges. And these are just the results of spiral arms occasionally passing through your sort of viewing point. And so this isn't really a turbulent broadening parameter so much as it is a feature that would shift your line based on when you're looking and how you're looking at the disk. But
do you break your horizontal velocity into azimuthal and radial?
Break it how exactly?
The horizontal is 2 components.
Right, so the way we do it is we subtract off, in this case, we subtract off an azimuthally averaged value, and then take that component and average it with the, so VR and V5. So and then we add them in quadrature. So
VR and V5 in acquisition, or?
That's a good question. I don't actually know. I think so, but I don't actually know. It's a good question. And you can also see, even in the case where you have these large spiral arms, you still have vertical velocities that are relatively uniform and smaller in value. Okay, so how do these two mechanisms compare? Well, they have similar turbulent values close to the disk midplane. If you consider at least the horizontal component, it's about a little above 0.01. Actually, this is slightly lower in the self-gravity case, but it's not terribly different. I wouldn't call that significant, but there is a significant difference in the vertical velocity component here. Right? But there's also this anisotropy that I pointed out before between the vertical and the horizontal velocities, whereas that does not exist in the MRI. case. So that, again, the self-gravity case, oh, and also the self-gravity case shows the presence of large spiral arms, which is not seen in the MRI calculations. You do see spiral density waves and that sort of thing, but nothing like these large spiral arms. But this is only for really large mass disks, which are probably unlikely to be the case for the systems that we would be observing. Okay, so what's next then? So sort of to tie it all together, well, the first thing is we do want to improve physics, continue our studies with ambipolar diffusion, and add in the Hall effect, because as you saw, it was a very dominant effect in intermediate densities, and we really don't even understand how that affects the MRI yet. And maybe add in improved ionization dust physics, although that's, I think, less important than getting these two things nailed down. Run some more sophisticated simulations, such as global MRI simulations, and do stuff like maybe raytracing for that, and a grid-based self-gravity calculation so that you can go and study higher distances away from the disk midplane. And then and the most important thing is to make comparisons between models and observations, and to test our predictions that we've made. And to do that, we will be looking at different species instead of just the CO rotational ladder, which will probe mainly the outer layers of the disk. We can look at the isotopologs and go and look at a deeper layer, and even the deuterated species, which can probe down to the midplane. So if we can use Meredith's method of extracting a turbulent value and look at different depths and then get an idea of what depth we're looking at, then we can get at the question of, well, how does it, and look at different inclination angles. So we would look at different disks with different inclination angles and make some assumption that they're all behaving sort of the same, and hopefully they have roughly the same masses. And so in that way, we can make a comparison and see, well, is there this gradient with height that the MRI predicts, and more specifically, is there a significant gradient which would represent like the presence of a dead zone? If we see a dead zone, that's sort of a smoking gun for the existence of the MRI. And being trained in the MRI, that's sort of what I'm hoping for. But being a scientist, I have to remain unbiased as best I can. So I would be happy to see either one. And so in the self-gravitating case, you would really be able to pick it out best. I mean, there needs to be more work, of course, done. But you would be able to pick it out best if you could do direct imaging and see large spiral arms, or if you were to look at this anisotropy between the velocity components for different systems. That one might be a little bit harder to pick out because you can't look at one system. Did you have a question?
Yeah, I did. I would just say, here's bias. So for the current observational state, so they're currently doing this with CO, mostly doing it with
Yeah.
So this is the CO, the other deuterated and the iso. I can't remember.
Yeah,
that's going to be done with ALMA.
Yeah, so that's why the whole thing flashed up on the screen. Or this is sort of the basis of our next thinking, is to look at these different species with ALMA, which will have better spatial resolutions, so we could potentially even get closer to the star and look for the dead zone there, which means that's a little bit more of a robust thing. Theorists definitely, in the MRI paradigm, think that there is a dead zone closer to the star. Not really close to the star, of course, where it's hot enough, but further away. And so, improved sensitivity, of course, but also improved spatial resolution. And so then finally, we could look into other potential turbulence driving mechanisms, such as maybe numerical instability is actually working, and maybe that has a unique signature. Can't rule out anything. Again, I like the MRI, but I have to be an unbiased scientist. This, there's a lot of debate about this. There's also the possibility of convection, which no one has completely ruled out yet. Although there's still a lot of debate about that, and maybe even some sort of velocity wave instability. I didn't talk about those because those are even less appreciated, I guess I would say, in the literature. So I am just about out of time, so I'll just leave these points up for you to read yourself, and I'll take questions now.
So the effect of alpha in your turbulent calculation gets as low as like 0.03
It's less than that. So the V over C was less than 0.1. So alpha would be the square root of that, or sorry, the square of that.
I wanted to ask, this is related to that, how exactly did you run the simulation? So what were the parameters that put you into the self-gravitating regime, and what was the evolution of the system?
Right, so since Duncan is the leader on this project, I'm probably not going to get all the details right, but it did start off with, I believe, a minimum mass solar nebula model. It included opacity, from like a Bellon-Lynn type of opacity, radiative transfer using both polytropic cooling as well as a flux-limited diffusion, 500,000 SPH particles, and then you just vary the initial disk mass. So I guess the profile probably followed the minimum mass solar nebula, but the mass was changed. I'd have to look again at our submitted paper. And I can, well, pending his permission, since he's lead author, I can send you a free
And
one.
was the mass changing much over the course of the simulation?
In the global simulations?
Yeah.
Well, we picked a regime where it was not. So it sort of shows a small window where things had settled down, but it hadn't, like creeped a lot onto the central distinct particle.
In the self-gravitating disks, shows there's a difference between Z and
Yeah.
horizontal.
Yeah.
I'm wondering if you could artificially suppress vertical self-gravity.
Mm-hmm.
Could you bring those velocities close together and have extra separation?
Artificially, I'm not sure what I understand what you mean by
Like
artificial.
switch GZ to 0.
Oh, you mean turn off vertical gravity? Or
Vertical self-gravity.
vertical self-gravity. What's that?
I don't know. That sounds really weird.
Well, it's also weird because I don't know if you can do it in SP.
I'm just wondering if this difference between VZ and the horizontal is due to the fact that that extra vertical self-gravity trying to
Oh, I see what you're saying.
accelerate.
So you're wondering if it's just that things are collapsing, are trying to collapse more in the midplane, but then you're driven by the shear draw. Things are also collapsing sort of in the horizontal plane, but then things are shearing that out and creating spiral arms that way. I mean, I think is that what you're saying more or less?
I'm just wondering why VZ is so low.
Well, that's sort of my idea, is that you don't have anything. I mean, this sort of spirally structure, and maybe Caitlin could comment on this if she knows more. I mean, I'm getting into the self-gravity business because I think it's very interesting, but she did her thesis on it. Just that, you have these spiral arm structures, and they tend to dominate, and there doesn't seem to be a lot of upward motion. And it could be, you're right, it could be because things want to slow it down and collapse. But you also do have thermal balance that's balancing that. So short answer, I don't know, but it might be worth thinking about. Caitlin, do you have any?
I haven't seen the paper yet, so
Okay.
it's hard.
It's not out yet. Thank you. Any other questions?
You didn't know that?
No?
Okay, well, let's thank Jake again